Okay, so today when we look at notes, we're going to be looking at vertical motion. The key to these story problems that we're talking about actually has nothing to do with being able to do story problems. Okay, you don't actually have to be able to read it and write an equation or do anything like that. What you need to be able to do is you need to know the different pieces of a quadratic. So guys, we're taking notes, headphones should be out. Okay, so we need to do some review from things that we were looking at before break with quadratics. Okay, we said, and this is the piece that you will need to write down and you will want to be able to access and look at. Okay, we said that if we were to graph a quadratic, it made what shape? The U shape, which we call a parabola. Okay, now the majority of the parabolas that we're going to be looking at today, because we're talking about vertical motion and gravity happens when we throw things, okay, are going to be upside down parabolas. They're going to open down. Okay, so when we graph a parabola like that, we're going to get something like this. Okay, this would be a parabola we would get if we were to graph using the graphing rules we talked about before break.
It's the arch.
Okay, right, and we said there were parts of this parabola that we could then label and talk about. Okay, one of the things that we said we could talk about was this very top point up here. What did we call this top point up here? Do you remember? Starts with a V.
Vertex.
The vertex. Okay, so the very top of this we call the vertex. Okay, if we want to find the vertex of a quadratic, okay, well, we had two options. If we didn't have the graph to start with, right, if we were only given the equation, if we were given the equation y equals ax squared plus bx plus c, right, we said we couldn't just find an h and a k because in this format there wasn't an h and a k. And so if we wanted to find the vertex, we had to do negative b over 2a and then to find the y value, we had to plug back in the x value. Nathan, please don't. Plug x back in. Now, let's just say we're talking about a problem that's talking about height of me throwing a ball. Okay, and my label down here is going to be time. And my label over here is going to be height. Is this my x-axis or my y-axis? Nathan, please don't. I don't want to ask again.
X.
This is my x. Okay, which means in my vertex, my x value is dealing with time. And in this situation, my y value would be dealing with height. Okay, those labels are going to be really important in a moment. Making sure we know how to get each of those pieces. Okay, what did we call this down here? Do we remember? What is this point on a graph?
The x point.
The x-intercept. And another name for an x-intercept was a root or a zero or a solution. Right? If we ask for an x-intercept, we could also just solve a quadratic. What formula did we use repeatedly to solve a quadratic? Yup, that one. What's that one called?
B plus.
Okay, so x equals negative b plus or minus b squared squared minus 4ac all over 2a, the quadratic formula. Let's just not even look for it and let's just write this down. On both ends. Do you understand?
I already found it.
Just stop. I really don't want to have to go this route.
Sorry.
Coming back from fall break.
Alright.
If we have this picture, we have enough information to do everything we are going to be looking at with vertical motion. Okay? I have it. Just leave it alone. So, you then have some problems that you have in notes. Right? That I typed up for you. Okay? Anything that is represented with an arch can be represented with a quadratic. So whether it's the curve on a roller coaster, whether it is the path a ball takes when thrown. Okay, now some things we don't realize are represented with a parabola, even though there's not a curved motion. For example, if I talk about gravitational pull,
That's a ball.
okay? So if I take a ball and I just hold it here and drop it,
It's gonna fall.
okay, it's gonna fall, right? It looks like it's going straight down.
It's gonna go above.
But if we were to graph that, time is also passing, which means it's actually going to be graphed with a curve. Okay, so if you can sort of consider, like, I always think of, you know, those heart monitor paper sheets that print out, right? And it just, all it is this thing moving up and down, but the paper is also moving across at the same time.
Remember like the graph on the earthquake? Polygraph? Yeah, like a polygraph.
Okay, no, a polygraph is a truth or lie detector, an earthquake is doing the vibrations of the ground. Okay, but if you're doing your heart rhythms,
But there's no like earthquake graph or like.
I know, it's talking about the
That's
vibrations.
My foot lowered the seat and it got stuck.
Okay, but if we would just sit still and we would be doing what we need to be doing,
can't sit
then we'd
still.
be okay.
I can't sit still. With disease.
Nathan,
What?
do we have the notes copied down?
Partially.
Okay, so everything that we're looking at up here is going to end up being represented with a curve and a parabola. So, if we look at number one, my students read these problems and think, well, I can't do this because I don't know these words, but just keep reading because it tells you what to do. Suppose a football player kicks a ball and gives it initial upward velocity. Usually my students get there and they stop reading.
Right.
Okay, of 48 feet per second. It's kind of important, but only kind of important.
It's like a point.
Because it then says the starting height of the football is 4 feet. We represent this width. It tells us how to put all of that information into an equation. So we don't actually have to write an equation from that information up above. It tells us what it looks like as a quadratic. And my students often want to know where this negative 16 comes from. This is gravitational pull.
-6.
Right? If you throw a ball, it is eventually going to hit the ground if no one catches it. Why? Gravity. Okay? So, when we look at this, we want to use that graph that we were just creating with the labels to answer each of these questions based on that equation. Okay, so when it says, if no one catches the ball, when will it hit the ground? Well, let's go back and look at our picture. Okay, if this is my picture, and here's someone standing here, and we have a football, okay, what happens to the football? Right, it goes up and then it comes back down. This is the path the football would take.
That's pretty high.
Okay, if no one catches it, when will it hit the ground? At what point on this graph is representing where the football hits the ground?
The x-intercept.
Over here, how do we calculate an x-intercept? The quadratic formula.
That's crazy.
Okay, so what this question is really asking is if no one no one catches the ball, when will it hit the ground? It's saying solve this with the quadratic formula.
So A would equal negative 16.
Well, what does A equal?
Negative 16. Or
A
zero.
equals negative 16. What does B equal?
48.
48. What does C equal?
4.
And so we would start plugging these values into the quadratic formula. So we would say negative 48 plus or minus, which we should be able to do this, at least the majority of us, because we already took this assessment. Okay, so B squared is 48 squared minus 4 times A is negative 16 times C, which is 4. If you haven't already taken the assessment, you should be paying attention because you'll still be doing the quadratic formula just like this on it. Okay, once we got this plugged into the quadratic formula, what did we do next?
You do the inside equation.
Right, we do the stuff underneath the square root. So you would pick up your calculator. And we would put in 48 squared minus 4 times negative 16 times 4. And now we're here. And what would we do next?
You would square the.
Take the square root of the 2560. See if
Is that
it's a
negative
perfect
32?
square. Do what?
Is that
Negative 32, right, 2 times negative 16. Okay, it is not a perfect square. 2,560 is not a perfect square. Okay, so we said before break
We would quit.
that we would prime factor and we would simplify unless, right, we looked at some story problems that were length and width and area. Unless we are talking about something that gets a label that isn't a square root option. It's not how we talk about it, right? When I say that something costs 4 square root $17, well, no, that's not how we talk about money, right? We talk about money as a decimal. Do we talk about time when it will hit the ground as a square root?
No.
No. So this is a time that it would be appropriate to decimal approximate. 2 decimal points. Hundredths position. So when we put it in our calculator, we get 50.596, which would really then round to 50.60. Okay, so now we'll have negative 48 plus or minus 50.60. Then what are we going to do? What do we do next with the quadratic formula?
Something. Oh wait.
Don't you plus and minus it?
Right? We need to consider both options. Okay, so now we're going to consider both options. So we need to do negative 48 plus 50.6 over negative 32. And negative 48 minus 50.6 all over negative 32. Guys, there are rules with leaving that 0 on there. We are just talking about a measurement. It doesn't really matter what we rounded to, so it's okay that we drop that 0. If this was like a science class and we wanted to show what we had rounded to, we would need that 0 on there.
Negative 49.6 and 46.
Make sure you hit equals in between.
What do you mean?
You need to do negative 48 plus 50.6 equals, because this is a negative 0.08.
How? What?
And this is a positive 3.08. Okay, what did I just find? What is that info? What does it tell me?
How long it take?
How long it takes for it to hit the ground. How many answers did I get?
2.
2 of them. Are they both correct?
No,
Why not?
because it's not in time.
What do you mean it's not in time for?
Negative 0.08 isn't.
Can time be negative 0.08 seconds?
No.
No, this is our not reasonable answer.
It's a pass.
Okay, so this one's not reasonable. What label are we putting on this 3.08?
Time.
And what is our time label in this one?
Another dot.
I heard it.
Second.
Seconds. So this is seconds. So if we throw the ball with that velocity and that starting height, or kick it or whatever, how long does it take for the ball to hit the ground? 3 seconds. Now, let's talk about what actually happens in a football game.
We lose.
Okay? If we want to punt the ball, depending on where we're at in the field, right? We want to get the ball as close to the end zone as we can, but also give our teammates as much time as possible to reach that point.
You can get high.
So you got to decide how much initial upward velocity do you want to give it while still not letting it go too far. Okay, now, does the actual football player sit around and do all that individual math?
Yes.
No, but coaches do. Coaches are looking at no more force, less force.
Tell me, Coach.
Those are the conversations that they are happening.
Coach Gilbert does this on a daily.
No, Coach Gilbert doesn't do this on a daily, but Coach Gilbert is talking about forces that they want to put on the ball. Any buddy here do a sport that they love and they do it a lot? With what sport?
Basketball.
Okay, so if you're but are you doing basketball with a regular training coach? I'm thinking about tennis where you're putting certain spins on the ball. Golf where you're hitting with certain velocities and certain angles.
Golf
I mean, right, we all play sports and we don't necessarily think about those pieces, but when you're doing that more in-depth training,
Does boxing have something like that?
No.
I don't know enough about boxing to know the answer to that question.
Polo. Water polo.
Water polo?
Okay?
What's so funny?
Are we okay with this being an answer?
Yeah.
What did this negative 0.08 seconds represent?
The negative?
Mm-hmm.
Like the block, like how high it goes?
Nope.
Dotted line.
It represents the x-intercept happening over here.
So the guy throwing it.
Well, it would be backwards in time.
So the guy not throwing
It's
it.
representing both intercepts of the parabola, even though the only part that's reasonable is the solid line. Okay? Question number 2. Says, when will the ball reach its maximum height? So we want to know when the ball will reach its maximum height. So let's go back to our picture. When is the ball at its maximum height?
At the vertex.
At the vertex. Which one of these is representing when?
The green. Or the height. Plug X.
Is this when?
No.
No, this is height.
It's negative B. That.
Time is when. So negative b over 2a is telling us when. So if we want to find when will it reach its maximum height, we want to do negative b over 2a. What did we say b would equal on this one?
48.
So we'll have negative 48 over 2 times negative 16.
So negative 48 over negative 32.
Yup. Which is positive 1.5?
Yeah.
Is that it? Is that what we got? So when will the ball reach its maximum height?
And 1.5 seconds.
In 1.5 seconds.
Yeah.
Right, this really isn't a difficult question as long as we have that picture to know what we need to do with it.
That's how high.
Question 3 says, how high does the ball go? Okay, so if we go back to our picture, what tells us where the highest height of the ball is? The vertex with the height. And so what does that tell us to do?
Plug X.
Plug x back in. We just got x. X was 1.5. So we're now going to plug that back into the original equation. Okay, so we'll say negative 16 times 1.5 squared plus 48 times 1.5 plus 4, right? This is just my original function rule. Negative 16x squared plus 48x plus 4. And I'm just plugging the 1.5 in for x. And you can like pick up your calculator and just type this in.
40.
40.
40
40.
meter.
What label is the 40 gonna get?
Meter.
Feet, because it's how high it goes. So this actually requires us to know nothing in addition to what we had already learned. Okay, it's just that we need to know which situation to use based on the question that it's asking. Does that make sense? Questions on those 3 pieces right there, A, B, and C?